General questions though? Any questions? No? All right, so this Thursday, we'll have a quiz. So that stuff I talked about last Thursday before the exam, that is what I will test, okay? So the mechanism of radical halogenation. So be able to know all the steps, including a termination step, if two radicals come together, okay? So you may have to reproduce all of it, or I may give you a little hint. I'll give you the structures, and you're going to tell me what are the arrows that gives me from the reactants to the product, okay? Maybe for some of them. But for some of them, I might just leave it, here's your reaction, show me the arrows, draw the product as well. And then, remember, we spent like 45 minutes, maybe up to an hour, doing that example where we predicted all the products of monochlorination. I could ask monochlorination, monofluorination, or monobromination. I'll give you the values for the rates, the relative reactivity, and you have to tell me what are the percent yields for all the monochlorination products. So that example we did in class, look at that, okay? So that actually, there's no examples of that in the homework. So your best bet here is the notes we went over in class, okay? Are there any questions about that before I move on? So nothing about cycloalkanes yet, no chair flips or whatever, no cycloalkanes, so no nomenclature. I will not ask any nomenclature. It's going to be strictly on radical halogenation, the mechanism, okay? And predicting the percent yields. All right, so any questions?
With the percent yields, you give us part of the information.
So I'll give you the relative rates, and then it's up to you to determine, exactly what the yields for each type of, mono product you'll get. Yeah. All right, so I think we left off, we were talking about the energies here. So last time we talked about ring strain and the relative heats of combustion based on cycloalkanes, okay? I'm not sure if we got to this page, but I'll just read it anyway. All right, so relative, did we talk about this relative stability of cycloalkanes?
Yes.
Okay, so we got to that part, right? So which one's the most stable? Oh, wait, so did we finish talking after that, those numbers I talked about? That chart? Well, it was ring size, right? I think so. Like we had ring size 3 to 8, and then we list all the energies. Yeah, okay. All right, because I named these subtitles a little bit the same. All right. So let's use that information. So out of that chart, you just need to know this order. Relative stability of cycloalkanes. Okay, so you have your ring structures here. We only care about 6, 5, 4, and 3. Okay, so based on what we talked last week, 6 is the best. So cyclohexane is like the golden standard. That's the most stable. So the stabilities are in this order. 5 and 6, relatively stable. 5 is not as stable as cyclohexane, but way more stable than butane and propane. Okay? So here we have the most strain. All right, so you have both, remember, torsional strain, and then when we try to compress bonds into a ring or atoms into a ring, that increases what we call bond strain. Okay, so most strain here, least stable. Well, remember how I said alkanes are not really reactive? Well, cyclopropane, you can actually just dump in an HCl and it will open right up. So that they're not very stable, okay? But you can't do that to cyclohexane, and that's because there's not as much strain, so least amount of strain, okay? And so this is more stable. All right, so that's good and bad. One, you can't really react it. So if this was like, if these structures were part of like disease, bacteria, viruses, not really much you can do to react with this. But if the molecules in us that we need them to maintain their structure and shape, good for us, not very reactive, okay? So that's kind of some pros and cons there. Okay, so now we're going to talk one by one from most reactive to least reactive, each of these shapes in detail, okay? So let's start first with the most reactive and the simplest ring, cyclopropane. Okay, cyclopropane, its reactivity is kind of shown by its shape, but its shape can be misleading. So let's talk a little bit about that. All right, so cyclopropane, least stable cycloalkane. All right. So let's just compare it to propane with the 3-carbon chain we saw before. All right. So if we look at one of these CC bonds, okay, so the CC bond, you have overlap with one carbon atom, good overlap with the other carbon, okay? So here you have good orbital overlap. And so by this definition, you have a strong bond. Okay, so that's when they're flexible. When they're not flexible, this bond, this kind of like bond overlap here is not going to be as great if it's in a ring. So now let's look at cyclopropane. So cyclopropane, because of the bond angles, it actually makes this this overlap not as good. So here the carbon atoms here, now they're kind of pointed at angles here. So let me just back up for a second here. Let me try to draw this like this. Yeah, I think that's a good way to put it, like this. So see here, the overlap is much less in the cyclopropane. So that's what we call poor orbital overlap. So that's a weaker bond. So poor overlap here. And so this will be a weak bond. And here, these orbitals are actually the hybrid orbitals that we talked about before. So in both of these, they're, well, the one on the left is sp3. The one on the right is a little more complicated. We say it's sp3, but it's actually not at all. But I'm not going to talk about that. That's a little advanced, okay? So we call these bonds, even though they're like single bonds, they're not straight sp3 hybridized orbitals. So we call them a little different. We call them bent bonds or banana bonds because they're bent like a banana. And so yeah, there's like a whole Wikipedia page about this. It goes into detail like what these bonds are and how they kind of differ from a traditional CC bond. Okay, and we'll talk about that based on the bond length that we'll see in a little bit. All right. So are any questions about the pictures there? So propane, typical CC bond. Cyclopropane, bent bonds. So that's why the overlap is poorer. And the bond is weaker, more reactive. Okay? All right. So now let's draw little pictures here to kind of describe what kind of strain is in cyclopropane. So let's draw carbon atoms here. All right. So we have 2 hydrogens on each carbon. Okay, like we saw before. All right, so what do you guys think the what do you think the bonds angle, so they're the bond angle for each of those carbon atoms, what angle do you think they are? They're not 120. Think about this is a triangle, right? All the angles must add up to what total? 180, okay? So the way we get that is, let me just write this briefly over here. So interior angle equals 180 times n minus 2 divided by n. Okay, where n is the number of carbon atoms, so number of C atoms. All right, so you don't need to memorize this formula, but this is where the angles come from. So I'm using this equation to figure out how much each of these angles are. All right, so how many carbon atoms are in there? 3. So n minus 2 will equal 1. So the total is 180. 180 degrees over 3. And if I calculate that, each angle should be 60. Yeah, so 60 degrees. Okay, so we're going to do the same equation for pentane, butane, and cyclohexane. Okay, so each of these angles is actually 60 degrees. And is that a problem for carbon right there? What do you guys think? So what kind of bond angles does, what are the bond angles right here in just regular propane if I have H and H here? Yeah, so around 110 degrees, right? So that's a 50-degree bond compression. So that requires a lot of energy. Okay, so there's going to be a lot of energy in cyclopropane just because of that. Okay, so that's where the angle strain comes from. So this right here is where we have maybe make more room. Bond angle strain. Okay, so we have bond angle strain. And because of that, this bond length is actually a little bit shorter than a typical carbon-carbon bond. All right, so you don't need to know exactly why that is, but that's what happens when you constrain the angles there. The bond length actually gets shorter, and that makes sense, right? Because we're forcing the atoms closer together in a ring. So it's a little bit shorter than a typical carbon-carbon bond, and then this bond length right here is roughly the same as we expect. And that's because they're outside of the ring. Like that. Okay. So, but what do you think the hydrogens are going to do? Are the hydrogens able to move? So this bond angle here is 115 degrees. But let me just make that a little clearer here. So this bond angle right here is 115 degrees. Okay. So we have one area of strain already, bond angle strain. And now there's going to be another one. So let's just redraw this triangle. But I'm just going to draw my best attempt at a model here. So let's do the carbon atoms. Okay. So here's my hydrogen, so a little smaller there. Hydrogen, hydrogen, and then hydrogen, and then hydrogen. Okay. And then here we're going to have another hydrogen right there. So these right here, okay, and these right here, these hydrogen atoms are going to interact. So what's that strain called? So not steric, but when two things kind of like eclipse, right? So that's our torsional strain, yeah. So these are both eclipsing strain or torsional strain. You could call them either or. Eclipsing interaction / strain. So we have two of them here. So you're going to see this between any two carbon atoms in the ring. So you actually have 4 more of these interactions on the adjacent carbon 2 between the other two the two other carbon atoms. Okay, so really cyclopropane, you can't wiggle it out to kind of avoid these interactions. So that's why this is the most reactive. Okay. All right. Are there any questions on those two strains? So we have eclipsing strain here, and then I'll circle this one. The other big one is bond angle strain. So that's the major one. Bond angle strain is the major component here that causes cyclopropane to be so reactive. All right. So let's summarize those two strains here. So ring strain. So this is what we call ring strain. Ring strain has 2 components. Angle strain. It's angle strain or bond angle strain. Those terms are interchangeable. Plus torsional strain. So bond angle strain comes from this triangle and the fact that each of these bond angles here is 60 degrees. So equilateral triangle. So you're going from 109.5 degrees to 60 degrees. All right. So that's a big bond compression here. So big compression right here. So that's not easy to do. So that's a lot of energy. And then torsional strain, let's draw a Newman projection. All right. So let's say we have this carbon. And then we're going to draw it to another carbon atom. Remember the Newman projection here. All right. So cyclopropane. Oh, wait, sorry. Let's not draw it that way. Let's draw it this way. All right. And then this carbon is actually bonded through the back to the other carbon in the cyclopropane. And then all of these are going to have eclipsing interactions. Okay, so like that. And then we have this other H in the back. So that's the back carbon. So you're going to have a set of eclipsing interactions here. Okay. So eclipsing. All right. So that's with cyclopropane. Too much strain going on. So so that's why it's very reactive, very unstable. Okay. All right. Are there any questions about this Newman projection? I know it looks kind of weird, and that's because we only have 3 carbon atoms, and we're trying to connect them together in a ring. So it's kind of hard to visualize for some people. Are there any questions? No. All right. So one thing I want you to keep in mind, lots of bond angle strain and torsional strain, can't avoid it. So torsional strain is going to be kind of common in all the rings. But here, unlike some of the other rings, cyclopropane is kind of just fixed. And that's because how small of a ring it is. It's not very flexible. Okay. So common questions here is be like, look at the ring and tell me what kind of strain there is. You could mention ring strain, and we would ask, specify what kind of strains there are. Angle strain and torsional strain. All right, so let's talk about cyclobutane. So ring, strain, and structure of cyclobutane. All right. So cyclobutane, you add one more carbon atom. You may be able to alleviate some of the strain, but there's still going to be some present. So we have a ring here. All right, so let's draw all the hydrogens, wedged and dashed. So it doesn't really matter like where you draw the wedge and dash. Just draw one on each carbon. All right. So let's talk a bit about this structure. So this is what we draw on paper, but in reality, cyclobutane does not look like this. Okay, so it's kind of flexible. So I will put here not actual structure. All right. Does not look like this. Okay? And the reason is, why do you think it won't look like this? What's wrong with the hydrogens? So we look at just a pair of neighboring carbon atoms, right? Are the hydrogens going to be staggered or eclipsed? What do you guys think? Eclipsed, right? So when they're right next to each other, there's no wiggle room, so they're going to be eclipsed, okay? So here, all hydrogens are eclipsed. Okay, what I mean by eclipsed is that if you look at two carbon atoms, those hydrogen atoms on both are going to be eclipsing each other. That's what I mean, okay? All right, so let's prepare to draw a, I don't know what to call this, paper airplane? Okay, so just bear with me here. Boom. All right, so we're going to have to draw it a little bit like this. All right, so yeah, it looks like a paper airplane or a cartoon bird here. So this is called the puckered conformation. Okay. So the reason why cyclobutane likes to do this, so we're kind of like taking one end of the square and kind of making one end, kind of go inward, and the other one kind of bending out a plane to create this 3D structure, okay? So when we do this, some of the strain that we just talked about is relieved, okay? So some torsional strain, okay, reduced. All right, so let's add a few more details here. So I'm just going to give you some structural information because we know this and we have studied this. So here I'm going to tell you that this bond length now is pretty similar to the one in propane. 1.1, about 1.11 angstroms. All right. So I need to draw like some blueprint here. So this cross section of these lines, what this represents is that I'm telling you that to get this structure, I looked at cyclobutane from bird's eye view, and I bent one end. I bent the angle when it was just planar up a bit. So that's what these lines represent, okay? So here is if we look at this angle here, this is about so it's not a lot, so it's not drawn to scale, 26-degree angle of bend, okay? All right. But here, if we, sorry, maybe I'll just draw in red so we can see this. So this angle right here, all right, so that's an angle. That's still going to be 88.5 degrees. So, what's wrong with that? Do we have any angle strain? What do you guys think? Remember, tetrahedral is what again? 109. Oh, we're at 88. Still no good. Okay, so that's still not good enough. All right, so that's still bond compression. Here, I guess, is what? Like more than 12 degrees, almost 20 degrees, right? It's somewhere around that number. So that's still bond angle strain. So we still have angle strain. So sorry, guys, if you want to write this somewhere where there's more room, feel free. Okay, so that's still angle strain, right? These hydrogens here. So this angle is still 107 degrees. So that's still, still around the same for cyclopropane right there. Well, actually, no, it's even more compressed now because we bent it out of the plane. So that's why it's more compressed, the bond angle there. Okay? All right. And then this CC bond distance, so this carbon-carbon bond length is 1.551 angstroms. All right, so that bond length's not too bad. It's a little longer than a typical carbon bond, but it's longer because we're kind of elongating this cyclobutane by putting it in this pucker state. All right, so that's the pucker state. All right, so don't worry, you don't have to really reproduce this, but I just want you to realize that this is what it does. It's not square, okay? So you should realize that it adopts a different conformation to reduce spring strain, okay? And now let's talk about how this reduces the strain in the molecule. So let's draw another molecular model picture. All right. So I'm going to draw this. It looks like a trapezoid. Like that. Okay. So hopefully I can draw these hydrogens right. So these are the hydrogens. Okay, so what it looks like here is the hydrogens are going to be interacting here, okay? So they are not drawn to scale, but what we can say here is that they are nearly eclipsed. So they're not eclipsing, but they're very close. But the fact that we are able to move it a bit and get out of that eclipsing interaction makes this form better, okay? So nearly eclipsing strain. All right, and then the other ones here, let's just draw like this, like so. All right, so I kind of want to draw like this to indicate that it's not eclipsing. So this one is also nearly eclipsing strain, but not quite, okay? All right, so that's cyclobutane. Are there any questions about that form? Okay. So cyclobutanes are actually prevalent in nature. There's like, you don't have to write this, but in natural products, there's a chain that looks like this. All right. So that's a series of cyclobutanes fused together. What do you think we call that? Any ideas? Common name. What does that look like? Like a common object you might use around your house.
Looks like a ladder.
Yeah, that's called ladder reins. So we just called that because it looks like a ladder. Okay? And there are some natural products too. I can't name it off the top of my head. Probably like pharmaceuticals. Stuff like that. All right? So cyclobutanes are everywhere here. All right. So that's called ladder reins. So we just add the word ladder, add the word alkane to it, ane, and then you got the ladder rein. Okay? All right. Any questions about cyclobutane? No? All right, so now let's go to cyclopentane. So we'll work our way up to cyclohexane. okay? And cyclohexane is where a bunch of these topics will expound on. And that's because cyclohexane has unique properties because of its flexibility. All right, so cyclopentane. All right, so for cyclopentane, not much to say here, but it has so don't worry about this one's interior bond angles, okay? They are larger than cyclobutane, but that's not where much of the bond there's bond angle strain because of the interior angles here, and there's eclipsing strain because of the hydrogens. Okay, so what this tends to do, it tends to undergoes a conformation change, where now it looks like this. So we call this the envelope. And it gets that name because part of it is kind of bent upwards and downwards like an open envelope, okay? An actual envelope, okay? So when it adopts this conformation, if we draw the molecular model, so let's draw that now. All right, so these small, larger spheres are the carbon atoms. If you want to color code them, be my guest, okay? Boom. All right, and then this one here, like that. All right, so we have smaller spheres for the hydrogens. All right, so what happens here is that these two interactions, they're so far apart that they are not considered eclipsing no more. So this is like our staggered conformation, but it's not exactly staggered either. Okay, and then right here, what we have. Okay. Boom. So these are the smaller hydrogen atoms. All right. So we have another interaction here. So this one here. So I know it's not drawn to scale, but these right here, we have minimized or minimal eclipsed or eclipsing strain, eclipse strain. That doesn't sound right, sorry. Eclipsing, sorry about that. Eclipsing strain. All right, so those hydrogens now are so far apart because of the additional carbon atom that has some more flexibility. Now there's no really minimal torsional strain here. Okay, so and then if we want, let's see here, maybe we could calculate the angles in cyclopentane. All right, so let's think about the cyclopentane example. So if we take 180, all right, times, all right, it was n minus 2, right? So what would n be in this case, this value?
5.
Yeah. Well, wait, let's see. So n minus 2 will be 5 minus 2, right? So that's 3. Okay. What's 180 times 3? Well, let's see. 18 times 2 is 36. Add 18 again. Is that 54? 540. And then if we do 540 degrees divided by 5, what do we get? Let's see. Oh, wait, maybe we could do that. Was it? 108. So it's 108. That's pretty close to 109.5. So not much bond angle strain. Okay. So each of these angles here, 108. degrees. So we have minimal angle strain. Remember, sp3, we typically want 109. Oops. So that's not too bad, okay? But we can go better. We can do better, okay? So there exists a structure, not cyclopentane, but it's better and it has virtually no strain, okay? Which one is that? Cyclohexane, okay? So cyclohexane, so a lot of people don't like cyclohexane, and that's because you have to draw chair structures. Well, I find it kind of motivating because I'll say this. If you not draw chair structures that resemble what I draw, I will mark you off for that. So bad drawings here, no, okay? So I've seen really bad ones, so no bad ones. So we're gonna practice and make sure the exam's not until like another month. Make sure we're good at this, okay? We always tell that to people, even at Davis, okay? So let's talk about cyclohexane. I'm not going to make you draw these structures, but chair structures, that's a must, okay? So now let's talk about cyclohexane. And the reason why we draw it is because so cyclopentane, cyclohexane are the most common cycloalkanes in nature, okay? Or in most of the compounds we'll see, okay? They'll always have like a 6-member ring, 5-member ring. Propanes and butanes are very rare, okay? So the reason why this one's so important, it's a strain-free cyclohexane. All right, so first let's start by comparing the planar structure. All right, so let's draw a hexagon. All right, so to illustrate that this is a planar view, I'm going to make this a little bit bolded to indicate that this is coming out at you, okay? All right, so let's do a few things here. H. All right, H. All right, and then these bonds are coming out at us, so H, and then H, okay? And now these bonds in the back, we can't see them, so they're pointing away from us. So sorry if my spacing is a little odd. So what I'm saying here is that those hydrogens there, they're pointing away and they're going towards the back. All right? So now let's number some of these atoms here. So 1, 2, 3, 4, 5, and 6. All right. So now let's use that same equation again and find the interior angles. All right, this time it's 4 times 180, okay? And that's 720 now. So that's a total of 720. So each of these bond angles is actually, as drawn, 120 degrees. Okay, so this bond angle here, that's 120 degrees. So it looks like in the planar view, we have now gone from 108 degrees in cyclopentane to now 120. So that's still too big, right? So for tetrahedral geometries, that's still considered bond angle strain, okay? So if we look at this structure now, so we have planar cyclohexane. All right, so two things, 100 degree bond angles. Okay, so this is bond angle strain, so that's still bad. Okay, and then what's wrong with the hydrogens? What's the other type of strain we worry about? Torsional strain. So we have 12 eclipsing hydrogens. Now, what I mean by 12 eclipsing hydrogens is that each hydrogen on that atom is going to eclipse a hydrogen atom that's on the adjacent carbon atoms on both sides. Okay? All right, so now what happens here is that, all right, so the chair structure, how the chair structure forms is you're taking the ends at one carbon and the fourth carbon, and you're doing this. So on the first carbon, we're going to take this and move down. So we're going to move this carbon down. So move down this carbon 1. And then at carbon 4, right here, move up. So it's kind of like you're taking both ends and you're kind of making it, doing a clockwise turn, counterclockwise turn of those carbons. And now it's going to look like this. Okay? All right, so to draw these, you need to just do practice. So just take a look how I draw it first. So like that, something like that. So practice, see if you can draw like that. If you can't do it the first time, that's okay. We'll just do more practice. All right, but that's the chair. So see, one end was kind of pushed down and up, and you can kind of see that in the sloping lines as I move horizontally. One's pointed down and one's rising up. So that's what I mean by up and down. So when you take those carbons and move them in the opposite directions, you're going to create this not so planar structure anymore. And just by moving the bonds that way, we actually remove all of the eclipsing interactions. Okay, and I'll show you in a bit in this diagram here. Okay, so there's a few things we have to draw here. So how do you draw the hydrogens? So on this structure, you should never add dashed or wedge bonds. Never. Okay, because this is a 3D structure. So when we draw the bonds, they are going to tell you 3D information. Okay, so how do I draw the hydrogens? So this is where I'm also really picky, okay? So if it doesn't look like a tetrahedral, I will mark it off, okay? So be careful. So here, so just draw the hydrogens, and then you see each carbon atom right here, right? Look at each carbon atom. That looks like a tetrahedral geometry, okay? So you don't want to do things like this. So you don't want to draw it like parallel to that, or you don't want to do it like straight like that. That will be considered wrong. Okay, so don't do that. So what you want to do is straight down here and then kind of curved upwards a bit so it looks like a tetrahedral. H, H. So the tricky ones are in the center, like these ones I'm going to talk about. Okay. Soon. Maybe that's telling us to take a break. We'll take a break after this. All right, like that. And I'll talk about what these positions are too, okay? So don't worry if you don't, like, why are we drawing it straight up? Why are we drawing it kind of like parallel? I'll explain that, okay? So, tetrahedral. So these are how you draw all the hydrogens on the chair structure. Okay, so let's add a few details here, like how does this change the geometry here? Okay, so each of this distance here is 1.121 angstroms. This bond length now is a normal bond length, almost 1.54 angstroms for the carbon-carbon bond. Okay, and then these bond angles here, very close to 107.5 degrees, so almost close to 109. And then this bond angle, even though this is not drawn to scale, this is still very close to 109.5 degrees. So here, virtually no angle strain. So very close. That's less than 2 degrees of a difference, whereas 108 was like 1.5. Very close now to the bond angles of tetrahedral geometry. So now no angle strain. Okay, so this is called the chair. Now, the reason I call it a chair, I don't really know. I think because the actual shape, it looks like a lawn chair, maybe. Maybe that's why. Or I think it just it just comes off the tongue a certain way when you say it, because cyclohexane, chair cyclohexane, you want to say block cyclohexane or something, so maybe that has to do with it, but I'm not exactly 100% sure. Okay, so here we have nearly tetrahedral bond angles. And then here, no eclipsing hydrogen. So I'll show you that in a minute. Okay. So if we look at the reason why we draw it this way, because it represents the no eclipsing strain. Okay, so look at this hydrogen here. So let's look at this carbon and this carbon. If we look at that, do the hydrogens look eclipsed or staggered? Staggered, right? So now let's maybe show that in a little different way here. So I'm going to draw the 3D model now. Okay, so. Are there any questions on this chair structure? Does it make sense that we move this side down, it points downwards, and then on the opposite side we moved it up, so now the point is pointing upwards? Does that make sense? Okay. Maybe after the break we take, I'll show a little video how these conformations form in real time. Okay. But let's just draw the 3D model now. So let's do the spheres here. Okay. Like that. I don't know, maybe drawing the spheres way is better for drawing the chair. I don't know, maybe. All right, so here's the hydrogens. What the hell are people talking about out there? All right, we'll just annotate this and take a little break. Maybe I have to close the door, actually. So see here, if we draw a Newman projection on these two carbon atoms, we will see that they're staggered, and I'll talk a little more about that later. But these right here are staggered conformation. Okay? All right. Let's take a 10-minute break, and then we'll continue talking about this, okay? I'll show a little video that kind of demonstrates how this forms. All right? All right, take 5, take 10 here. Why does the light go?
I took it from my dad.
Thank you. There we go.
Are you gonna have us like draw the 3D model?
No.
No.
You mean with the spheres?
Yeah.
No.
Okay. Yeah, so. Oh.
You guys still hang out or anything?
How do you think though?
Just try. Oh yeah. What's up?
Like still young, and it hasn't been that much since I was new. She's just kind of horrible, but she realizes she was
Oh my gosh, they're crazy too.
Yeah, I mean, yeah, I don't even want to worry about that 4 year.
Yeah, it's a small dog, or a little dog. It's still.
He's pretty decent size, but I think he's like 12 minutes.
It's like a medium size, and then the
He's like 25 pounds. So it's like,
yeah, it's a pretty
I mean,
big.
he is pretty chunky. He's overweight for sure. But like, I think his box was like actually food.
Oh, of course.
And he's like, I would say 10 years size, honestly. He's cute. So like, he might have some like cattle dog mixes. His paws are all white with like mottled like brown black spots on him. So we think he has some cattle dog mix in him, which is like why he's so high energy. But like, female dog loves him so much that she's been like snapping at him and like fighting him, and we're worried that she's gonna kill him.
Yeah.
And we're like, okay, she's like, well, how great is she? And we have to see. And it's like, he's acting like this.
Yeah,
I don't know for sure because I've never had female dogs. And also, I think my housemate wasn't like fully selling him because she was like, he's cute, she likes him, but like, she doesn't think he's still him.
Yeah.
She like needs to be 100% because she lost her dog 2 years ago. So.
Yeah. This is like 2 feet in. Do you think he's gonna just have us do like the first structure? Some of them has to 3D. I think these two.
I'm gonna try with the model kits are a lot better at explaining stuff that I used to. So.
Yeah, I think I'm gonna do the same to understand like the body and like.
Yeah, it's kind of interesting. Like, so what she did with the
Amazon. But for like the equation, this is what I got confused on. Why is it 3? Or isn't it the number of carbons?
Because it's 5 minus 2.
Oh, I gave you your
Okay.
And so it's like yours equation 180 equals like n, which is the number of carbons.
Yeah, but it's pretty cold in here, so yeah.
Divided by
Go ahead. Okay.
I'm like halfway.
Does she have any tickets for 9 years picture?
Yeah. Yeah, like into line.
Hell yeah, that's like 2 hours all day.
But I find I send them, I study update.
Oh, what's up?
Are you gonna get to drawing the like most stable conformation and the least stable?
Yeah, I think we should. Mhm.
Okay, because that's what we were gonna do in essay.
Yeah, sure.
I
We'll get
wasn't
to
sure
it.
if I was gonna get like 2 ahead or.
No, I mean, if you get, if you show it right away, I mean, they know it's chair structure, so you kind of show them that.
Okay.
I think they'll be more comfortable, getting started on that. I think that'll be best.
Okay, my chair structures are not great.
That's all right. As long as it looks something like that, you're fine.
Okay.
Yeah. Huh? Okay. Yeah.
Which one moves up and which one moves down? Is this up or is this down? It's up.
That's down. That's up.
Oh, not this one?
That's down too. This one's down. That one's up.
So down, down.
Yeah. You got it.
Yeah, we need mine.
Yes.
I would write it as more electromagnetic, that's why it's more stable.
Mm-hmm.
And there's already because of like this, like the oxygen. You want to write like, is that right?
Yeah.
Okay,
All right, let's get started here. So let's continue where we left off. Not from like 2 weeks ago. All right, everyone sign in. Okay. All right. All right. All right, let's continue. So, before we continue, let's see how the bulk conformation comes about. So let me just go back to our concepts here. Let's see. Let's look at cyclohexane analysis here. All right. All right, so let's see here. I think this one goes over how to draw them. So if you're having trouble drawing them.
Hi, welcome to this short
All right, let's just listen
animation
to
of
it.
making a cyclohexane chair conformation line drawing. Being able to draw this conformation is essential for solving many organic chemistry and biochemistry problems. Let's bring in a ball and stick model of the chair conformation of cyclohexane and rotate the model where 2 metal carbons are in the foreground and 2 are in
so
the
you can kind
background.
of see the chair, that chair shape.
This is the orientation we
If you
need for
rotate
making
it.
the line drawing. In order to better visualize this for our drawing, let's convert this to a stick model. Let's also remove the carbon-hydrogen bonds, leaving the carbon framework. Let's now start to draw our line drawing. You may want to follow along on paper or a tablet with the drawing on the screen. By changing the color of the central carbon-carbon bonds in the foreground and the background to yellow, we see that these are parallel to one another.
Yeah, so they're all parallel.
Let's draw lines on the right of the screen to
So you
represent
draw a series
these
of
2
parallel lines.
yellow
It's
bonds.
easier to draw, but I never draw it that way. So
Back to our stick model. Let's turn 2 more of the
Well, it
ring
helps for
bonds that are
beginners.
parallel to red. Let's draw these on our line drawing now. We will turn our final 2 remaining parallel bonds to green on our stick model. Let's complete the line drawing with those. We will now turn all of the bonds, both on our stick model and line drawing, to black. If you have been following this on your tablet and your line drawing looks like the one on the screen, congratulations. we have the carbon framework completed. Let's reproduce this line drawing for the next part of this animation, placing one above and one below on the screen. To complete our line drawings, we need to draw in all of the carbon-hydrogen bonds. Let's now place a dotted line through the stick model and our line drawings. The carbon-hydrogen bonds that are parallel to this dotted line are the axial hydrogens. On our stick models, we will reveal the 3 carbon-hydrogen bonds that point up from the 3 carbons that point up. On our top line drawing, we will now draw these 3 carbon-hydrogen bonds. Likewise, we will reveal the 3 carbon-hydrogen bonds that point down from those 3 carbons that point down. On our top line drawing, let's draw these 3 bonds. Now for the equatorial hydrogens. On our stick model, we will hide the axial hydrogen positions now. Let's place the previous bond colors, yellow, red, and green, back on this stick model and do the same with the bottom line drawing. Now we will show the right and left carbon-hydrogen equatorial bonds. Let's turn these to yellow to indicate that they are parallel to the yellow ring bonds. We will place these 2 bonds on our bottom line drawing now, parallel to the yellow ring bonds. On our stick model, we will show the 2 carbon-hydrogen red bonds that are parallel to the red ring bonds. On our bottom line drawing, let's draw these 2 red carbon-hydrogen bonds. The remaining carbon-hydrogen bonds are parallel to the remaining carbon-carbon green bonds in the ring, so we will show these as green in color on our stick model. On our line drawing, let's draw these 2 green carbon-hydrogen bonds. For the equatorial hydrogens, note that the 3 carbons to the right of the dotted line have equatorial hydrogens facing to the right. The 3 left carbons have equatorial hydrogens facing to the left.
Yeah.
If we superimpose these 2 line drawings, we now have a completed cyclohexane chair conformation. Cyclohexane's chair conformation is the lowest potential energy form.
Let's not talk more about that yet. All right, so that's how you draw it. So those like the equatorial ones, those are harder to draw, but they're parallel to a set of parallel bonds in the structure. But by practicing drawing these and drawing out all the hydrogens, you should be able to reproduce. Well, I've been showing you as well. All right, so let's go over, not drawing, but the conformations here. How do they form here? Okay. So hopefully this one. So these are some intermediate conformations. We won't talk about these yet. I'll probably talk about them on Thursday. But if you look at, let's see, there's one with no narration. Let's see. Oh yeah, here it is. That's fine. All right. So those are some of the conformations we'll talk about, okay? So, but the most important one is our chairs and boat. Those are the ones we usually talk about here. But see, there's many different conformations until it reaches the chair. So at first, the half chair, that's where you just raise one end first. Then it goes using a series of letter conformations. And then the chair is the lowest energy one. So that's how we get to that conformation. Okay. Are there any questions about that? Any questions about the conformations? How it kind of, this flexible structure goes through all these different shapes? Nope. All right.
Did you say that the chair conformation is the lowest energy?
Yeah, that's why I showed you that one first. Yes. Okay. So that's the lowest energy one. Right. All right. So okay. So now what we're going to talk about, practice drawing more chairs, okay? So we're going to do the conformers of cyclohexane now. Okay. So we can draw, this is what we say the chair conformers. And for chair conformers, the bonds we draw, they're classified to axial and equatorial positions. Okay, so let's just draw our generic chair structure here. All right, so the thing about axial positions, they're always in the same direction every first and third carbon. So 1, 2, 3. Okay, then 1, 2, 3. So those are all up. And then the ones that are down, 1, 2, 3. 1, 2, 3 right there. And I drew it, I kind of drew it in perspective there, so that one's going down, okay? So these are called the axial bonds. So these are the axial bonds. And we call them axial because if you think about the Earth here, they're parallel to the Earth's axis. Okay, so they're parallel to Earth's axis of rotation. So that's why it's axial, okay? And now then here I'm going to use some different colors. So let me just do the equatorial positions now. So red. And then let's do black here. Blue. Blue. Oops, not blue. Red. All right, so we have 3 sets of parallel bonds. So the bonds are parallel every third bond over, I guess. Okay, so so now I'm going to draw the equatorial positions that are parallel to a series of 2 lines. Okay, so you have this one parallel to the red. So let's write this as equatorial, just equatorial, okay? So this bond corresponds to this parallel bond. So that's the equatorial position, okay? All right, and then all these red ones as well. So this is an equatorial hydrogen, all right? And so these all match. They're parallel to all of those bonds in red. So that's equatorial. That's the first set of equatorial bonds, okay? Then we have the blue ones, okay? So the blue ones here, you're going to have this one right there. So let's just write this as equatorial 2, equatorial 2. This one right here, equatorial 2. So there we drew one line there. So now there's going to be another bond here that's parallel to these lines. And this is equatorial 2 as well. Okay, so I'm just color coding them so you know the lines that I draw, what other lines they're parallel to. Okay? And then lastly, we have the black positions here. And these are also parallel. Okay? So, you got that one. And this one. So I might have to draw this one out a little bit. Okay? So that one, equatorial 3, and these are parallel to a series of 2 lines here, equatorial 3 and then equatorial 3 right here. Okay, so the way to draw this is, well, I think if you just practice this a couple times, this procedure will become more normal. But just know that they should be parallel. If we look at a couple of these lines, right? Like this one, this one, this one. They're parallel to a bond, one bond over. Okay, so you have this bond, go skip a bond and look at the next bond. On either side, it should be parallel to that bond in the chair. Okay, and we see that by these highlighted portions there. Okay, and you can do that for any type of these equatorial hydrogens. So those are the equatorial positions. Because if you look this on a side view, we saw the chair, right? So we look on that side view, this is actually the equatorial position. So equatorial bonds here. Okay, so they're in line with Earth's equator. So if you think about the Earth here, right, and a sphere, this is a sphere. Okay, the equator is the horizontal axis, right? So if you kind of look on the side there, these bonds are kind of extending along the line of the equator. So that's why they're called equatorial. Okay? So the only times you'll have to really remember these terms is when we talk about stability of chair structures. You're like, oh, you know, the substituent is not in the axial position, so there's no strain involved. Okay? So when substituents are in the equatorial position, that's the most stable, okay? Because you're going to avoid certain interactions. Okay. Are any questions about equatorial axial bonds? We kind of just have to practice drawing some of these. It'll make more sense when we draw these structures. And we kind of look at them in models again on Thursday. Okay. So let's talk about ring flip. Okay. So for any chair conformation, they can do what we call a ring flip. So when we say ring flip, we're not like flipping it over itself. It might look like that's what's happening, but that's not the case. Okay. So what's happening here is a part of the molecule, one of the bonds is going up and down, and then in a chair flip, it's vice versa. Okay? So I'll show you an example. Let's draw this chair structure. All right, so let me just mark this green. All right, so here's hydrogen A, axial position, position 4. And then this one position, that's in the equatorial. Okay. So you're going to do a flip here. So we call this a ring flip. Cyclohexane is the only one that does it. So here we're going to move C4 up. So, I don't understand why I say C4, carbon number 4, okay? And then here, in the red, well, let's just show this. We're going to move C1 down a bit, okay? All right. So, how you draw a chair flip is you're pretty much going to draw the chair structure where the left side now is pointing up, and the right end is pointing down, okay? So it looks like this. So this is the tricky part. Drawing the chair structures in both directions pretty easily, okay? All right. Now, this is where it gets tricky here. So let me just clarify my notes a bit. All right. Okay, so this is why I color coded it because I'm going to use these labels in the same. Okay. All right. So any ring flip, thing we have to remember: things that were axial are now equatorial. So that's what it means by flip. The stereochemistry is the same. Whatever's pointing down, it's still going to be pointing down, but it's going to go from an equatorial position to an axial position. And that's kind of the confusing part, okay? So if I keep track of where 1 was, let's say this is number 1, okay? Well, was that bond pointing down or pointing up on the left? Downward, let's toward downwards, right? So let's use this as upwards, this towards downwards. So yes. So it's still going to point down, but it's going to be axial this time. So 1 looks like that. Okay? And then the green one, which is number 4 here. Well, on number 4 on the left, it was also down, right? But axial. Now it's equatorial. Don't draw this too close. Let's just move this a little bit. Like that. Okay? All right. The other thing about chairs you have to worry about is that certain positions are flipped. Okay? So let me just explain here. All right. So let's look at this blue position. All right. So this blue position is now actually right there, I think. Let me double check though. Okay. So let me just verify here. So these two positions, they will swap. Okay. In this chair flexion, now they are here and here. Okay. But when we do more examples, I'll explain this a little bit more better when we do more examples, okay? And then this position, this actually shows up. These two switch too, okay? So these two are going to be switched as well. So they, if there were substituents here, it'd be a lot clearer. But the two circles, two color circles I indicated, and the other chair structure, they swap places, okay? It's not like, carbon 4, that's like the apex or the top of the peak or the top of the point where they meet on 4 on the right. Those stay the same, right? And then the point where they meet on number 1, that's the same point pointing down in the right structure. But the circles there, they actually don't stay the same when you go to the next structure. They swap places. And it has to do because those are the points where the bonds are moving up and down to create the other chair structure. Okay? So hopefully we won't have to, that won't be too confusing. But when we see some other examples, when we see di-substituted cyclohexanes, hopefully that's a little bit more clear. Okay? But I just want to point that out. So let's just give these some numbers here. So if this was, I don't know, C, D, E, F. E is here now. F is there now. And then C is, this is D, and that's C. Okay? So see, they kind of swap places there. All right, but let's not talk a little more about that yet. Let's talk about the stabilities of the cyclohexane ring structures. Okay, so now let's talk about interactions. Okay, so there's one major interaction we have to worry about. That is called 1,3. So let's just put it right here, 1,3. Yeah, what's up?
How come when we flip the ring, why does C and D both stay the same?
Well, they're the same positions, but if you it's kind of hard to explain. So they switch positions because of the bonds that are moving up and down. So one of those bonds, say bond, the position D, that's the bond that's kind of going down now into the chair structure. On the right, it's going down. And C was kind of pointing up, but now it's going down in the structure. So that's why it looks like that.
In the drawing, you have that many completely switching places there.
Like that label, like the label you still the same with C and D in both positions, but yet
Yeah.
E and F have swapped in both of their rings.
Yeah, E, let's see here. Yeah, maybe that one I should have swapped too. So let's swap that.
So basically they're staying.
Yeah, so E is now here. Wait. Yeah, no. E is here, and F should be there. Did I have it backwards?
Yes.
Okay. No, sorry. Yeah. It's confusing with all substituents. So we'll show this more when there's actually substituents there. It'll show how they shift. Okay? But that's how the positions are. So if you were to draw, so this will be important when we draw rings with two substituents. All right? So the easiest thing to do is a 1-4 relationship because they're at the ends. And no matter what you do in either chair structures, those substituents will always be at the ends, and they won't look like they migrate to two different, bends and folds up, like rising folds, diving bends in the structure. So I think those are the easiest to name. So 1-4, like you have 1,4 dimethyl something. Those are the easiest to draw for for chair flips. Okay, but good question. This will definitely come up because these are confusing. Okay, but now let's switch gears here. Let's talk about gauche interactions. All right. So what this means is if you draw a chair structure here, all right, so the axial positions, that's where we see interactions, okay? Okay, so if we have all these axial positions, they are going to interact with each other and cause strain in the molecule, okay? So that's where we get all these gauche interactions. And you have that on the top of the face of the ring and the bottom here. So you also have it on the bottom here, here, and here. So all of these are interacting with each other. So that's 1,3 diaxial strain. So we call it 1,3 because if you look at these substituents here, they're always at the one position, 2, 3. 1, 2, 3. So you always see a 1-3 relationship here. That's why it's called diaxial strain. They're both in the axial position and they'll interact. Okay? So now let's convert this to a Newman projection. All right. So let's put this in blue. I'm going to write this in blue. H. And then this will help you, this will help us when we're looking at the Newman projection. Okay, so let's number it now. 1, 2, 3, 4, 5, and 6. All right. All right, so you guys draw 2 circles relatively close to each other like this. All right. So we're looking at this perspective down the 1-2 bond. Okay, so let's label this as carbon 1. So we're going to draw H here. H, okay. So this is 1. On the back carbon is 2. And then we're going to get these H's here. All right. So the tricky part of this is you have to connect these 2 circles. So it looks like a cyclohexane and it's not linear. Okay, it's cyclic. So what we can do here is, this is my first carbon, so this is the part in blue. Okay, and then the one coming out over here, this CH2, that's my carbon 6. So let's label this 6. Number 6 right there. Okay, and then we connect it like that. Well, actually, sorry. I don't want to use black anymore. There we go. H. So this is now carbon 5 in the front because look right here, right? It's in the front. Okay, so that's carbon 5. All right, so carbon 5's there. That means the back carbon here is 4, and it's going to be staggered because it's in the chair conformation. And then we get to the back carbon, which is the back CH2 in red in the back there. So here's the CH2, boom, and it's right there, sticking in the back. That's why I drew it like that. Okay, So what can we say about this arrangement? Is it eclipsed or is it staggered? Staggered. So that's why the chair form is preferred. Everything is staggered. The other forms I showed you in that little video, the conformations are slightly not staggered, or they're fully eclipsed, or they're steric hindrance. Okay? So here we have a staggered arrangement. Lowest energy, most stable. All right, so you won't necessarily have to draw a Newman projection like this, but it's often helpful to show how 1-3 diaxial strain, how that's a problem, because that's a gauche interaction. Remember gauche interaction? There was some steric hindrance. That's the reason why. Okay, so that's one of the major strains in chairs. So that's why only one chair form is preferred most of the time if you have bulky substituents or substituted branches that are carbon atoms or not hydrogen, basically. Okay? All right, so let's talk about, let's do a few more drawings here. And then, so this is where I'm going to say which chair here is more stable. Okay, that's what I'm going to end at. And then on Thursday, we'll talk about di-substituted cycloalkanes. Okay, cyclohexane. Sorry. All right. So now let's draw a line here. We're going to do something similar, and we'll end there today. Okay, 1-3 diaxial interactions in substituted cyclohexanes. All right, so what if the substituent is in axial position? All right, so axial position, you have 1-3 diaxial strain. All right, we call it strain, we call it interaction. They're pretty much, they're interchangeable here. All right, so let's draw our chair structure again, and we're going to use the same numbering scheme that we saw before. Okay, so I'm going to draw all the bonds. CH3, H, H, H. All right, so I'm just going to draw them on the ends here, not at the center. Just for clarity, okay? All right, so now we're still going to look at this end. So here's my eye, here's my perspective, looking towards that end. All right, so now let's draw the Newman projection here. Okay. So at the 1 position, there's a CH3 sticking out axial on the bottom. Okay. Now, let's draw this carbon as 6. All right, sorry, that's very lopsided. Like that. All right. Okay. Well, I did this better on my notes, so the fact I can't reproduce it is kind of sad. Okay. So right there. Okay, so let's number. I guess I didn't number this one first. So let's do it in red, so it's clear. 1, 2, 3, 4, 5, 6. All right, so we got 1 here, 2 in the back. All right, and 2, we have a hydrogen sticking out right there. Oh, maybe I could just leave it black. H, and then here we have carbon number 3. So we have 1, 2 in the back. This is coming in the back. So this position is 3. And then in the back carbon here is 4, and then in the front carbon, that's 5, okay? Now let's draw the rest of the hydrogens in. There's a hydrogen on carbon 4 going in the back like that, and then one sticking up like this, okay? Now let's look at carbon number 3 here, stick all the way in the back. These two hydrogens here and this methyl group, if we drew out the methyl group hydrogens, well, I won't draw it. We just drew it already. But you see here, this is now going to interact with this methyl group. Okay? So when the substituent is in the axial position, it's going to interact with an H on the cyclohexane ring. Okay? So that's called 1,3 diaxial gauche. Remember gauche, one that looks like they're all staggered, right? But there's still some steric hindrance because the carbon groups are close together. So that's the interaction here. All right. So this form right here is less stable. And why? Because of that ghost interactions, okay? So even though it's in the chair form, they're not always stable, okay? Now, what do you think happens if that was equatorial? Will we have that same interaction, you think? Let's find out, okay? So now let's do this scenario. Substituent in the equatorial position. Oh, yeah, sure. So if we have an equatorial position, we actually won't see this interaction at all. And that's why a common question for this is draw the most stable chair, draw both chair conformers and circle the one that's more stable. And you can always say that the most stable one is where this interaction I just drawn is avoided. And that one is avoided if this methyl group here was in the equatorial position. So if we do a chair flip, we'll see that, okay? All right, but I'm not going to draw a chair flip here. I'm just going to draw a normal chair conformation, and I'm going to show the substituent in the equatorial position. All right. So let's just draw the chair first. All right, again, instead of in the axial, I'm going to draw it reverse. Now it's pointing upwards. It's now in the equatorial position. Okay, so I'm just going to draw these H's for clarity because that's going to show up in the Newman projection. All right, and then again, let's number our carbons. 1, 2, 3, 4, 5, 6. All right, so we are going to view on their perspective again. Carbon down the 1-2 bond, carbon-carbon bond. Okay. All right, I'll draw them a lot closer this time so I don't mess up. All right, so carbon 1, now the H is pointing down. The methyl group is sticking up to the right. Okay, so now let's just draw here. All right. So let's just draw all the bonds first. Okay, so this one, let's come over here. Remember there's these two H's now? In the back here. Okay, so now the back carbon, all the H's are staggered. And now we can number the carbons again. 1, 2, 3, 4, 5, 6. But look at these H's. There's no bulky carbon group now. So there's no 1 degree diaxial interactions because the methyl group there is not in the axial position, it's in the equatorial position. Okay, so here we have no 1 degree diaxial gauche interactions. Okay, so this is the more stable conformer. So this is more stable. So more in the equatorial position. So if you're in the equatorial positions, you're more stable because there's no gauche steric hindrance interactions. All right, that'll be it for today. We'll pick up on predicting which is a more stable conformer for dye substituted conformations on Thursday. Okay?